Can you see the screen now?
Yes.
Thank you, Dr. Maiti, for this nice introduction about myself. And I'm very much delighted to be here. Though it's very, very early morning here. And yesterday I had a very short talk with Dr. Maiti that I cannot make it because it's too early. And here the sun rises only at 7:40 and now it is 6:40. But I think anyway, it's a pleasure for me. So I will start my talk today, and I know the overall theme of this, your FDP is the sensor technology, and I had the previous experience with working in the gas sensors and the holographic sensors and also the BIPB. So right now I am actually engaged how I can or we can actually create BIPB as a sensors, and I thought this is a very good platform to present my talk, and I can explain what we are trying to do as a BIPB and how it can work as a sensor. I will give very overview, not very in-depth, the way you guys probably work with the sensors, with the sensitivities and analysis. But this will tell you whether you can actually work with the BIPB as a sensor or not, and if it is, then what are the scenario. So again, I'm Dr. Aritra Ghosh from Renewable Energy, University of Exeter, Pendrin, Cornwall, UK. This is the location, and these are the two very nice building of my university. And thank you, the Mizoram University, for inviting me. Today, I will talk about our little bit about my university and my group, and then what is the building energy and why we need the integration of photovoltaics into the building. Then a very small talk about the intelligent building and how BIPB can work as a sensor and what are the challenges and the solution, and then future application for the BIPB. And finally, I will conclude and recommend some future work. This is the UK map, and UK is a combination of the England, Scotland. This is the Northern Ireland, and this part is the Wales, and this is the London. And I am from this segment, which is the Exeter and Plymouth one. Exeter has basically two campuses. One is in Exeter main campus here, and then we have another campus in Cornwall, which is a very nice and beautiful part of the UK. This is the most touristic area. This is the total number of students currently enrolled in our university from different 130 countries, and our rank is 12 in the UK. And our department is one of the oldest renewable energy course in the UK, and it started back in 2003. I think Dr. Mathi already said about myself, so I will not go deep in this topic. So this is my academic and professional background. These are my research activity, but honestly, I do teaching because I feel that this is our responsibility to convey the message to the new students, so that what we are doing. That is the reason I take classes for the first year solar energy, second year energy management, fourth year is the project, and then masters and MH. We in UK generally we don't have MTech or MTech courses. We generally call it the Master of Science, and I take the Smart Window and the BIPB course for them. This is my broad area of interest. I work with the building energy, smart window, particularly daylighting and thermal analysis, then phase change materials and a lot of different other materials. This is some of my supervision activities. This is our research group, which is called the Solar Energy Research Group, which is led by Professor Tapas Malik, who does work with the concentrating solar or photovoltaics. We have another lecturer, Dr. Asif Tahir, who does work with the materials for storage, hydrogen generation, photocatalysis. We have Dr. Santhal, who does work with the fabrication of second and third generation photovoltaic technologies. And finally, this is myself. I do work with the overall building energy efficiency calculation if you have a lot of other different material and how you can integrate them into the building. Now, as I first introduced BIPB as a sensor, so here I'm throwing the question whether it is possible or not, because we know that in the sensor probably we need input signal, and then it will sense and you will get some output response, right? With my 10 years experience in the BIPB and with the working with the pressure sensors with the holographic, I found that probably our BIPB can also work as a sensor, because It takes the solar radiation, then it can sense something and it can generate the power, right? So now the question is that, is it really feasible? And if it is, then how? Before jumping into this BIPB as a sensor, I thought it will be good that if I tell something about the brief about the background of the why the BIPB came into the market. So at the beginning, you know that there is a very much the global energy consumption issue, because in 1973 our coal consumption was somewhere 25% and it is still 27% in 2018. And because of this higher consumption, we also produce a lot of greenhouse gas emission, and that is the reason we are actually making our earth is very warm, and we are melting the ice, and all those issues are already known. We know that. These are some report from the United Nations, and they're saying that within these 100 years, our sea level rose by 19 centimeter, and we are actually daily and every day we can say that we are increasing our Earth's temperature. And this is the number of ice losses happened from 1994, and this is 65%, and the amount is actually very much, if you think about 100-meter thick sheet of ice, which is size of the UK. So this is not a very ignorable area. And the most drastic impact probably is the on the global death because of this burning fossil fuel. In 2018, nearly 8 million people died because of these issues, and in 2016 it was 4.2 million. And if you see this chart, which is comparing from 1990 to 2013, that most of the Asia Pacific and African country and Latin America, this percentage actually increased, whereas little improvement we can see in Northern America and the Europe and the Central Asia. So to deal with this problem, so we can say that we have a trouble, right? So if we consume more fossil fuel, we have this environmental issue. So what is the solution? Can we actually stop to use this energy consumption? This is a very nice graph which shows that if we actually do that, we will probably go back to our origin, where it is in the forest. So this is telling that when we didn't have the industry, we didn't have the power consumption or the coal or the oil, we are in this forest, and then we increased our civilization, and this is the best location or the best part of our life where we actually send people into the space. And then if we still use now, if we stop that, we'll probably go back here. To deal with this climate energy issues, our world leaders created the United Nations, and right now they are dealing with that. Okay, we can meet every 5 years, and we can set some target, and then we'll just review the target. And the last year was the time where they were supposed to meet in Glasgow in UK, but due to this COVID, they delayed the meeting. And this year in November, they will again meet and they'll review the what they actually proposed back in 2015. So this United Nations and most of the countries right now in the favor of the renewable energy, and I am particularly interested in the solar energy, where you have the solar cells or photovoltaic system which take the sunlight and produce the green energy. Now you may probably heard there are a lot of issues with the solar energy, but we are actually growing. And if you see this map, which is from IEA, International Energy Association, they're saying that in 2019 our PV installed capacity actually reached 617 gigawatt, and we are expecting over 5,000, okay, by 2050 or more than that. So slowly but steadily, our PV integration is happening, and the installed capacity is improving. So this is a good sign that we are actually dealing nicely with these global climate issues. But the problem is that how you actually integrate this photovoltaic technology or the PV power generation. So there are two different ways. First one is that you can just keep your photovoltaic system on the ground, or you can say the ground mounted PV, or you can use the roof mounted PV, okay? And this roof mounted PV, you can either say the building integrated or BIPV or building attached or applied. I will talk more about later what is the difference of this BIPV technology and the building integrated photovoltaics one. Now the question comes why we are actually integrating photovoltaics into the building. So what are the reasons to do this roof mounted? We can easily implement everything on the ground, right? So the first reason is that the land, because our PV is not that much efficient. Like a photovoltaic system can be only 13 to 14% efficient fully, and the amount of power we need now, and if we want to take everything from only the photovoltaics, the amount of photovoltaics requirement is huge, and we cannot uh, use all the lands. And also some countries like in UK and EU, we don't have that much land. So, and also due to the urbanization, the number of buildings will increase in the city. So in the city area, you cannot have any land to use the photovoltaic system. So, and also, so that is the reason you can choose your building where you can install the photovoltaics, and that will actually also reduce the transmission and distribution losses. As I think most of you are from the electrical or electronics background, you know that how crucial is that to reduce those losses. Okay. And another is for particularly BIPV technology, it actually offset the building material cost. So this is a very crucial part, and that is the reason most of this UK and EU or US, we are very much interested about the BIPV compared to the Indian counterpart. So we can actually integrate photovoltaics in two different ways. First one is the building integrated photovoltaics, and second is the building applied photovoltaics, and this is called BIPV, and the first one is the BIPV. In case of the BIPV, it is actually not very traditional photovoltaic system what you actually see in your general life or in the road or in the building. In particular, BIPV is the made glass PV glass system, which is you can consider your system as a window system, the window you have in your house, which is made by the single glass. It can replace your tiles and also other parts such as roof and window or shading element. And not only the power generation, it has the property which can control the solar heat light and also the heat loss and heat gain. For one example here, you can use your BIPV as a window system, you can use BIPV as your wall system, you can BIPV as a roof system. In case of the building attached or applied one, it is not like a BIPV. You just buy the traditional photovoltaics module and just integrate on your roof as a rack mounted or the roof mounted. And this is my campus. And because of the new government rules, if you create a new building, you have to use actually the photovoltaic system on the roof. So this is the UK rules now. And you can see that for the BIPV technology, the main job is actually to generate the power, not only but whereas in BIPV it has other part, like you have to think about the light transmission, the heat transmission, and also the power generation. So we can say that our BIPV system has the multifunctional property. So if you consider your BIPV as your traditional window system, it has the solar light is coming, and it's depends on the transmission of your system. It can actually reduce or reject the light, and there is a heat losses happening from the outside and inside surfaces. So these are the five property which you have to consider when you are talking about the BIPV technology. The first is the U value technology, U value, then you have the solar heat gain coefficient, then you have the daylight glare, and then you have the power generation. So these five factors are the very crucial part when you are talking about the BIPV, but this is not the part when you are talking about the BIPV. So BIPV, we just only consider the power generation. Now, why I'm talking too much about the building or the BIPV? Obviously, I said about the land use, but there is also another factors. The other factors are the consumption of energy from the building sector. Okay, so you can say that in 2018, the building sector consumed 36% of energy, which is a very high amount. And because of that, energy is coming from obviously the fossil fuel. We're actually generating very high amount of energy, the greenhouse gas emission from the building sector, which is 39%. So building itself is a sector where we actually consume a lot of energy. So the question comes, why building consume energy? So the first question is, the first answer probably, we have to think that why we need the energy for the building. So generally, if this is a building and this is like us, we need a pretty comfortable temperature to work inside the building, and that is generally between 18 to 20 degrees centigrade, or is the light level should be 500 to 2000 lux. Now we have the solar radiation, right? So throughout the day, solar radiation varies, and depends on the country, this amount actually changes also. So as we have the solar radiation, it has also heat and light, but still we need the energy. Why? Because The when the heat exchange is actually coming through these building envelopes, it actually stored inside the building, and depends on the location. Sometimes it just increase the room temperature or decrease the room temperature, because if it is a cold climate, most of the heat actually flows out from the building to outside. So you can see the window has a very high significant losses, because this is a transparent and it has a very low U value. Sorry, a very high U value. So to maintain the inside temperature of this amount, we need either air condition in summer climate like in India, or in room heater like in UK. So that is the reason we consume a lot of energy, and that is the reason building consume energy. So this is just a very brief comparison between a very hot climate and a very cold climate. So in cold climate, this is if you compare this UK or European country, we need mostly we need the heat for the space heating, whereas in the India or the hot climate, mainly we need the heat for the energy for the air conditioning load. So now there is as United Nations again created and asked most of the countries that you should have some target to reduce also the building sector. And now these are the target made by most of the countries, such as in UK, we have a target by 2050, we have to be, building has to be zero emission. That means whatever we use in the building, that should not create any CO2 emission. And EU also has target, and US also has target, but India and China, we don't have any target from that side. But India has a target, suppose like by 2022 we have to reach that much amount of the PV power generation. Now, wondering what is the currently India status? Probably all of you maybe know that India has, this is the energy generation segment from the in India, where coal has the most contribution. And also India has a target, as I mentioned, that 100 gigawatt, whereas 60 is ground mounted and 40 is the roof mounted. You can see that India has also some built integrated system, but this system is not the BIPB technology, it is the BAPB technology for India, but you can actually use the BIPB also, so you have free choice. Now, these are the typical photovoltaic system which you can use for your BIPB or BAPB technology. Fast is the first generation, which is based on the crystalline silicon. This is the most, I think, the stable system and commercially available, though it has some efficiency limit. Then we have the second generation, which is this CIGS, CDT, and amorphous silicon. And basically, this system came into the market to enable the use of the BIPB technology, because the crystalline silicon based systems are very much opaque, whereas you can make this system a semi-transparent one. And currently these are very much hot research topic, which is the third generations dye-sensitized solar cells and the perovskites, because within the 10 years they reached the amount of efficiency which actually crystalline silicon took 30 years to reach. So that is the major reason. Probably I think this technology is actually very famous now in Oxford University and one university in Korea. They are doing jointly work, and maybe we are expecting that in 10 years it can be a standard commercial system. So we can see that BIPV has a promising solution for the building energy, and also because of that, this BIPV market is actually growing, and we can expect that by 2026 it will probably nearly 6 billion USD. Now the question comes again, so BIPV can actually solve all the building energy issues? The answer can be the no. BIPV alone cannot solve all the solution. Because of that, actually right now there are a lot of other systems are coming. So this is if you consider a building which is actually you want to make it a zero energy building, and because of the presence of a lot of smart technologies, you can say this is an intelligent building, because you have the building energy management system. This is if you consider your roof is made by the photovoltaic system. Then there is a smart window technology. When you give the power supply, it became transparent. When you don't give the power supply, it became opaque. So you can use your window system with this smart window one. So by making it opaque, you can actually block the daylight coming inside the building. That means you can control the heat gain of your building. So this is the overall system where you have a lot of different other technologies and which can work very efficiently to maintain your inside temperature, such as your building energy management system can tell us that when it is a very hot and sunny day, it can trigger the smart window into a very low transmittance state so that it will actually reject or stop all the light to come inside. Then you have your ambient temperature is low, you can activate your heat pump or air condition, depends on your own criteria. And if it is your excess energy is coming from the PV, you can send them to storage or the grid. Or if you have the based on your occupant comfort level, because comfort is a very much a variable parameter, right? I can say that I can't actually stay with 18 or 20 now because of my 10 years of staying here. I need only to be comfortable state, I need only 15 degree. But some people who are in a very hot climate, they need probably 20 or 30 degree. So depends on your own criteria. Building energy management system can set all those parameter and changes the color of the window and activate these heat pumps or HVAC. Now, to activate this building energy management system, we need a lot of sensors, right? Sensors for the temperature, sensors for the light, sensors for the humidity, and sensors for the wind. Then only it can actually work nicely. Now, my question our group right now is focusing whether we can actually eliminate all those sensors, because the presence of all those sensors actually create or make this system very complicated. Sometimes if some sensors actually doesn't work nicely, all those systems actually falls. So the our question is that can BIPB can actually being alone act as a sensors, and how? Because we know that BIPB has a very standard rating. When you buy the BIPB or the photovoltaic cells, we know that at 1000 watt per meter square or 25 degrees centigrade, it has a standard power, and then depends on the different solar radiation or the incident light, the variation occurs for the power and also the current and voltage. So if you see about the 9 a.m., 10 a.m., 11 a.m., when there is a variable solar radiation, you will have a variable power and the variable current and voltage. Can we actually feed those parameters into the building energy management system and tells that, okay, now we have to do this job and you have to do that another job? So this is the question we are right now trying to solve. But the challenge we are facing is enormous challenges out there with the BIPV technologies, and we have actually sorted out 4 key challenges. First is the performance of photovoltaic technology at high temperature. What are the issues? Then if it is a snow or dust covered, how it gonna work? And if it has a static transparency, how it gonna work? And then obviously the major challenge is the lack of standard for the BIPV installation. So I will talk first about the first challenge, which is the performance at high temperature. Probably you know that on the silicon solar cells or even the second generation, they don't work nicely at high temperature. So at the beginning, they will work nicely, and then when the ambient temperature or the material temperature increased, the power actually degrade. And this is very drastic, or at first you can say for the crystalline silicon solar cell, and little less for the thin film. Now, suppose your building energy management system is set that when uh, you have the high solar radiation, so the PV will generate the high current and voltage, and that will feed to the building energy management system, and then it will automatically switch off the window. Now, at certain point, at high temperature, your PV power degrades, and then that means your signal will go in different other way and in very wrong way, and then maybe you don't need to switch off or switch on those things, and it will just create some trouble. So this is another issue based on the sensors, but we cannot just work for the sensor, because our other ambition or BIPV or BIPB is to generate the power, and for that reason we have to some point actually to reduce the temperature. And particularly for the third generation solar cells, this is also very complicated, though these cells are not that much standardized yet. But we can see their power generation or the power degradation is actually very varying, like it's kind of a swinging nature. So suppose like this is a perovskite solar cell. At low temperature, it actually generates high, and then at the standard one, it actually becomes stable. And then again, if you increase the temperature, it degrades the power. Same happens with the DSSC one. So we don't know if we use, suppose your building energy management system is set for crystalline silicon solar cell, then if you change with the second generation or the third generation, whether you have to set up all those things newly or Like, we still don't know what we have to do with that. We are still working because most of the perovskite solar cells are not standard. If you change a lot of different material, this behavior will actually also vary. So to have the solution from this high temperature, we generally use the passive methods like natural cooling or the phase change material, whereas for the BIPB technology, we use the active airflow or the water flow. So this is the solution to increase the power generation from the photovoltaics, but to act as a sensor, we still have to go very long way. The second trouble is the dust cover, which is probably the very promising issue for India. And here the issue with actually with the snow, and these are the collected different samples from the globally, and we can see that almost everything, whatever actually falls upon on the photovoltaic system, it actually creates some obstacle of the light, and that means you actually depends on the different deposition level. You actually can see that there is a change of the transmission, and transmission, like on the top of the photovoltaic solar cell there is a glass, and it depends on the light intensity. That means if the presence of dust actually decrease the light intensity, it actually decrease the power generation. So it is a very much linear relation. So if the transmission drops, that means you are actually your power generation also drops. These are the different level of of the soiling or the dust cover losses globally. And India, as I'm right now involved in different projects in India, we can see that there is a different level of soiling losses. You can see that from the month to month and or year to year also. So this is a did test in IIT KGP campus, and within these 2 months you can see how much changes happen. It is for crystalline silicon, the losses nearly 35% power losses. For perovskite and DCs is also nearly 34 and 34%. So the power losses can create another issue due to the due to the dust cover. And in case of the snow covered, which is a very much, I think, very common issues in northern part of Europe and also the northern part of UK. But in the winter time, your BIPB is fully covered with the snow, and you actually, and that time, maybe it cannot work as a nice sensors because you are not getting any light inside your or on the top of the solar cell. And even a very 10 centimeter snowpack can reduce your the light transmission nearly 5%. So this is a huge losses happens. So what is the solution to get rid of from this the dust and snow? We can actually clean the photovoltaic technology, but we have to be very cautious that we can actually clean when only our cleaning cost is very low. So such as manual cleaning is only feasible in the developing country, not in this country, but you can use, like for snow, you can use the hot water. There is another new material technology is happening. This is called the self-cleaning coating. It can be hydrophilic, hydrophobic, or isophobic. So what happens, you can actually so we can see that you can create some coating on the top of this material, and due to the presence of that coating, when your dust or snow fall upon on the photovoltaics, it just roll down. So this is another solution, but again, challenge is that none of these technologies are actually very much standard yet. So that means you cannot say that whether you can use this manual cleaning or the use of water or the self cleaning. So we still have to go a long way with this system issues. The third challenge is the privacy. So as I said, our BIPB is the semi-transparent or transparent. Now, if you consider a Middle East country where privacy is the main application or the main requirement, you cannot use the photovoltaic technology in that way because again, you have to use the curtain to block the light or something. And if you use if you use this technology for those climate or those country, it's very hard. So what is the solution to have the privacy? Suppose you have the photovoltaic first generation solar cells. So as you know, the solar cells are very much dark, and to have the light transmission, you can actually create some space between the solar cells and you can allow the light, but you cannot get completely privacy from this system, right? If you use the second generation, you can see that the more you will make it transparent, it is good. You can see through, but you will reduce the power also. But again, to have the full privacy, you need some sort of other external arrangement. To have the solution for that, we in our lab we have created addition of these two technologies. So where we are actually using the smart window and the BIPB in addition. So you can, when you need, you can actually just give the power supply, which can actually come from the photovoltaic devices, and then it will create the system completely transparent, and you can create the opaque system. So though this bus bar is not looking good, but we can actually get rid of by using another material. But this is just a proof of the concept we have created in our lab. So this is another solution with the addition of the smart window and the photovoltaic. Then our fourth, I guess this is the most crucial challenge, is the lack of standard, because our BIPB system, we have to use that in the building. Now, if your building is a new building, you can create very easily, you can install a lot of systems, sensors and anything. But if you think about your building is a retrofit building, which is already there and the structural loads are already predefined. Now, if you add the photovoltaic system, which is actually very much create a huge load on the building. So this is called, so can you actually install a lot of photovoltaic system onto a building? So this is a very crucial question. And also there is a question like whether if it is full of with the live loads, how it gonna work. And so we have to think probably to create the flexible photovoltaics, and that is the reason we have to think like when you were talking about the building integrated photovoltaics, probably we have to think more about the specific power. And also you have to think there is the rules for the fire safety, noise cancellation criteria, all those issues which are related to building code. There is a very good solution to add the photovoltaic system into a building, because if your building is full of covered with the photovoltaics and you have the excess power, now there is a high demand of inclusion of electric vehicles into the transport sector. So suppose you have a battery electric vehicles car, and if you create your settings, your car sets, and your roof is made by the photovoltaics, and you can actually charge your car by using that. So not only BIPB as a sensor, you can actually, so fast BIPB actually can act as a power generating system, and then it can actually work as a sensor, right? So this is another good solution of having the photovoltaics into a building or into your office building. The future solution in particularly in this country, there is like people right now not interested to add this blue color photovoltaic technology, and that is the reason last 10 years there is a new improvement of the photovoltaics, where the researchers are trying to hide the functionality of photovoltaics, and then they are adding different anti-reflecting coating to change the color of the top of the photovoltaic. So see, these are all of the photovoltaic systems, but because of the different texture, you cannot actually tell that this is actually the photovoltaic system, right? Though the efficiency is lower than the traditional one, but this is also very high in demand. So now if you use this system, you don't know how whether they will actually act as a very nice sensor or not. So I think this is the most obvious question I always get from what is the cost of using the photovoltaics? Is it a cheap? Is it a good one? You have to know that when you are talking about the BIPV systems or any photovoltaic system, there are two different costs. One is the soft cost, one is the cost for the instrument. Cost for the instrument includes the cost for the module, cost for the inverter, electrical wiring cost, and all those technical parts. But the soft cost is actually the very important, which we don't consider, which is the supply chain cost. So cost for the installation, the labor cost for the relevant permits, cost for the overall cost of the system or the marketing. Now, these things is actually going down, and these things actually depends on the policy of the government. So if the government actually wants to spread out the use of the BIPV system or BAPV system, they should have to think about this cost, and this cost actually enhance with the generator and also with the scientists. They know that how to reduce this one, but we don't have any power to reduce this cost. So we can say that yes, there is a promising, because if you see these graphs that when it was made by 10 years ago, we can see that the prediction of the cost was too high in 2024 or 2026, but it is actually went down even below that much of the difference. So daily, because of the invention of the new material or the new technology, the cost of the photovoltaics is actually going down. And this is the very promising aspect, we can say that, and we should promote more and more this BIPB or BIPB technology, so that we can have a very good or promising solution. So finally, these are some example of how you can integrate your photovoltaics. This happens in Finland, where they integrate the photovoltaics into the balcony. And I think in India, most of the houses we have the balconies. We can think about it. This is another. I don't think this is a very much aesthetic one, but they also did that one. And I think most of our Indian university have this long corridor having this balcony system. We can use the photovoltaics there also. This is a very good municipal corporation office in Spain somewhere. This is another way to integrate the photovoltaics into building. This is one shopping mall in Japan, where they actually use the scrap silicon solar cell to create this shopping mall. And this is another building in Park. This is the Apple headquarters in California, where they use all the roof made by the photovoltaic system. And this is probably one of the biggest solar photovoltaic roofs in the world. So you can see that how these things is actually coming into the market slowly. This is another south-facing vertical wall building in UK, in Manchester, where this is a CIS tower, and this is cladded by the photovoltaic panels or BIPB technology. And lastly, this is our India. In India, somewhere in Delhi, there is a fast zero energy building where they have used the building attached or applied photovoltaics, and these buildings only gets the power from this photovoltaic system. So this is a fully zero emission, zero energy building. So we can think about to use that system as a sensors, right? So what is the overall conclusion is that yes, BIPB has a potential to work as a sensors, but first we have to get rid of all those challenges associated with that. And obviously to integrate more and more BIPB into the building, we need a support from firstly, obviously, mainly from the government, and there is a very good or strong correlation we need between the government, building code officials, researcher, manufacturers, builders, and architects. So government can create the plans, and based on that plans, the building code official create the codes, and they can ask the researcher, okay, this is our requirement, and you just make the system, and we can work on that. Then we can send that to manufacturer, and then in conjunction with the builder and architect, we can actually implement this system into the building. So finally, if you are interested to read more and more about the BIPB and how it can work as a sensor and other technology, this is my recent paper, and that is the paper I also wrote for the Indian context. You can have a read that. And finally, I want to thank Dr. Maiti and all the members of the Mizoram University and all the listeners. And these are my funders and all my past researchers and my research group members. And finally, I want to thank and I want to stop my presentation. Thank you.
Thank you, Dr. Ghosh. Participants, if you have any question, please write in the chat box or question and answer section. If you have any question, otherwise you can contact with your email also. His email, and also in ResearchGate also, he is prompt to give the reply immediately. He is giving reply in the ResearchGate also. So you can you can contact also directly if you have any questions. One question has come, sir, that is giving that, thank you, sir, since solar cell perform an important role here, can you provide a details of limitation in efficiency enhancement of pin heterojunction solar cell? How do we overcome those problems?
Thank you for the question. I don't really work with the heterojunction solar cells, so I cannot tell exactly the way, but I think right now I think the major limitation they're trying to overcome, not on the based on the material development, what they're trying to do, they're using the concentrate on the top of the heterojunction solar cell, because they can actually I think they can sustain at very high temperature. So if you use high concentrated, suppose 200x or 100x, you can use the heterojunction solar cell, and overall you can improve the power generation. But exactly, I cannot tell how you can improve the efficiency because I'm not expert in the heterojunction solar cell. Thanks.
Question is there?
No, sir, I have no question. I have seen that the presentation is very good. Means it is very, I think the participants will get avenues from your lecture. So thank you, sir, for your invaluable time. And attendees are not making question. However, they can contact with, as sir has told, they can contact you over ResearchGate or over mail. Whoever is interested.
I'm always available. Just ping me. If I have some, if I know your queries or answer, I will definitely answer you. No worries.
Definitely. That should be restricted in your field, obviously. So, sir, thank you, I think, for your invaluable time, and you have managed some time for us in spite of your busy schedule. So we are really honored. It's our pleasure, sir. So if the attendees have not any other question,
I can add that again. I can ask for the sorry because
no, it's okay. It's okay.
morning sleeping, I have disturbed that early morning sleeping.
No, that's okay. I am really glad because you know, it's a very good connection with you. And I want to particularly say Dr. Maiti that I know him only for 1 year, but I think throughout the ResearchGate we talk a lot about the research collaboration and project application. I think when the COVID things will go away,
Yes,
and when I will travel to India, I really want to travel to a university and
yes,
your
sir.
research lab to see and to
It
meet the people.
thank you, sir. Thank you, sir.
Always welcome, sir. It is minimum that Mizoram. If you will come for means Aizawl city for a short duration, you will get good environment here.
Yes, sir.
Till now, it's a totally greenery and also with pollution less place, and there is a lots of advantage, and it's like a tourism place is there.
I would love to go there, and that is my plan to go there for a certain point. And yes,
Definitely, sir.
I
Most
miss.
welcome, sir. Most welcome, sir.
Thank you. Thank you for the invitation.
Okay.
I really want to go.
Okay, thank you, sir.
Okay, thank you then.
Okay.
So,
Okay, sir.
so I can leave.
Yes.
Yes,
Okay,
sir.
thank you. Bye. Thanks.
Bye.